Welcome everyone to our final session on control theory and applications. It's my pleasure to introduce our plenary speaker, Professor Kalen Belta. Professor Belta is with Boston University, where he's the director of the BU Robotics Lab and of the Center for Autonomous and Robotic Systems. And there's also a link between LITS and Professor Belta, not just through collaborations with multiple faculty here, but also through several of his former students who are current LITS postdocs. Professor Belta's work is mainly in dynamics and control theory, in particular in hybrid and cyber-physical systems, formal synthesis and verification, and robotics. And for this work he was also awarded multiple awards, among which the NSF Career Award and an IEEE Fellowship. So let's welcome Professor Belta.
Thank you, and thank you for the invitation again. So I'm going to talk about controlling dynamical system using formal methods. I'm going to start with a very short introduction to formal methods, and then I'm going to give a bit of motivation for the use of formal methods in the study of dynamical systems, and then I'm going to go into the technical part of the talk. And it's not as technical as the talk before. I'm not going to use the Blackboard. I have slides, so it's a bit more high level. So if you have technical questions, you can just stop and ask. So I'm going to introduce formal methods through a textbook example in formal methods, literally taken from this excellent textbook by Crystal Bayer and Peter Katun. So this is a sequential circuit with 3 logical gates and a registry. And I have a specification which says that if the input becomes 1 infinitely many times, then the same is true about the output. And the question is to check whether all the possible behaviors, all the possible executions of the circuit, which I'm going to call process, satisfies the specification or not. So in order to answer this question, I'm going to go through a number of steps. First, I'm going to formalize the spec. So in this particular case, it takes the form of a formula in a certain temporal logic, which in this case happens to be linear temporal logic. And I'm going to come back to this and explain it a bit more. But I guess we can see this color coding from plain English to the formula. We have a logical implication here, the if-then, and these are obviously temporal operators. This is always, this is eventually, so always says for all points in time, in the future something will happen, which translates in English to infinitely often. And again, I'm going to come back to this. And then next step is to write down a mathematical model for my system, for my process. And in this case, it takes the form of a final state transition graph or a final state transition system. It has 4 states because the input and the registry evaluate to 0 and 1. And then these arrows show transitions, and they capture all the possible changes that can happen asynchronously in the circuit. This one corresponds, for example, for the case when the input switched for 0 to 1, but the registry did not have time to switch to 1. This happens in the next one, and so on. And I'm also assuming that I start in a state where the value of the registry is 0, so this is what those incoming arrows show. The system is the model is initiated there. And since my spec is over x and y, not about, don't say anything about r, so it's like an internal system, I'm going to label the states to know whether x and y are 1 at those states. So then the problem becomes to checking whether all the possible runs, executions of this model satisfy the specification. So that's the classical model checking or verification problem. And this is how this book actually starts. So again, if you're a controls person, dynamical person, robotics person, you might think that this problem is trivial because this model looks very, very simple, right? It's like a finitely many states, finitely many transitions. But in fact, if you look carefully, the semantics of time is infinite here. So I want to look, it's in non-bounded time, and also because of the loops in here and the cycles, there's actually infinitely many infinite executions. So there's no way I can write down all the executions and parse them against this formula and check satisfaction or not. So you got to do something smarter. So that's what people in model checking do, in formal verification. So I'm going to contrast this example with an example from robotics, from dynamics. Again, cannibalized from my textbook, car-like robot. The spec is to driving from an initial point to a final point. The goal is to generate a control strategy to make this happen. So I'm going to show similar steps, but I'm going to emphasize the differences. So I have to write down a mathematical model. So in this case, it looks fundamentally different. It's a continuous time, continuous space, nonlinear dynamical system. And then the spec, I formalize it as a stabilization problem. Hopefully I can make B an asymptotically stable equilibrium, and then I want to make A as part of a Bayesian of attraction, and then use some sort of a gradient-based control to go there. Right, so there's the problem to generate a control strategy using these types of techniques. So I'm going to put these two problems side by side. I want to argue for the fact that there are applications that in the formal methods example that I showed, we have simple dynamical models, right? So if you write down a mathematical model for let's say, a circuit like this, or for a short piece of code, right? You just look at the values of the program counter, there's finitely many of them, you put them in a graph, and then you add transitions, which can be sequentially going through the code, they have go-to instructions. It's going to be some finite graph, right? So they should, from a dynamical system point of view, you think of a simple model. However, they use, especially in formal methods, very rich specification languages, such as temporal logics, and I can show you more complicated, richer specifications than this. Versus in the robotics example, we had a complicated system, and it can look more complicated than that. But specification languages are usually poor, right? If you're a control theorist, when you give your specification for your system, you want to stabilize somewhere. If you're more sophisticated, you might want to specify safety as an invariant set, but you don't have the richness of temporal logics. So what I want to do for the next 3 or 4 slides, I want to argue for the need to have something here on the diagonal. My point is that you want to be able to analyze and control possibly complex systems from rich specifications. So here's one example. Think of a disaster relief scenario where you want to deploy a robot such that you keep on taking photos infinitely often from an area of interest where you might have survivors or gas leaks. And then after you take the photos, you want to go and upload, and you give the robot a choice to upload whatever it decides it's better to upload. So this will be the first part of the spec, and then let's say that while you do that, you can use a sensor like a camera to look down and look for some rather local events such as survivors or fires and react to them accordingly. So the question is, how can you deploy a dynamical system like this, which can be quite complicated, right? It's a 12-dimensional dynamical system, strongly nonlinear, from a rich specification like this, right? So we're on the diagonal of that diagram that I showed you. And I'm actually going to come back to this, and I'm going to show a solution to this problem. I also have a movie running in here. And first we're going to look at this problem in this ideal case where we assume perfect controllers, perfect sensors. And again, I said I'm going to come back to this later in the talk. Here's a more realistic version of a more or less the same problem. So in reality, you don't have very precise actuators and sensors, but rather you have noisy sensors, and hopefully if you have a probabilistic model of your sensor, you can maintain a probability distribution over what you're looking for. Say you look for fire, then you can maintain a probability distribution over where you think fire is. So everything becomes probabilistic. The maps are usually unknown, and then you have to localize yourself on the map, and then so we have some results I just want to show off here a little bit and show you some this is an example in which you deploy a team, or actually one ground robot from a specification like this, but also we build the map with a team of robots and also do localization on a map that's built, while at the same time having a probabilistic guarantee to satisfy a spec like this. But again, this is not going to be part of this talk. And the problem can be even more complicated. So there might be the case that you don't know the dynamics of your robot, you don't know the environment, and you still might want to be able to deal with this sort of rich specifications. Like for example, this is an example from our lab in which we make toast with Baxter. So in this example, you can use temporal logics to specify some prior information that you might have to help the robot during the learning process. Like for example, in order to make toast, you tell the robot you have to pick up the toast and then put it in the toaster and then push the lever, right? So that's the useful information that actually we use to shape the reward that's used in machine learning, and it's done much more efficiently. Or even better, I think there are some concepts in the formal methods that I think are useful for machine learning. For example, let's say that you use these types of tools to learn policies for specific simpler tasks. And then there is a well-defined notion of compositionality for such objects in formal methods. The idea is that can you then compose them to achieve policies for complicated tasks without having to relearn. So again, we have some preliminary results on this, but I'm not going to talk about it in this talk. What I'm going to show in this talk towards the end is another example, which again shows a large dynamical system and a complicated spec. This is from a project we had with actually people from California, so the California Department of Transportation. We kind of convinced them this type of specs make sense, and I guess you can be convinced too, right? You always want to be free of congestion, you don't have congestions. And then you can want to have all sorts of liveness properties, like a link becomes, the car moves on a certain link infinitely, let's say, with certain deadlines, like wouldn't be stuck for more than 3 minutes, and then let's say you have a bridge, you want to make sure that you never have more than a certain number of cars on that bridge, because otherwise it's going to collapse and so on. Right, so again, this resembles temporal logic the way I showed you before. This is quite complicated. This has 53 links. When you write down a mathematical model for this, it's a 53-dimensional, in this particular case, discrete time piecewise affine system. So totally non-trivial system and rich spec. So again, the question that we're asking is how can we generate provably correct control strategies? So this is the outline of the talk. First of all, I'm going to give a short introduction to formal methods for finite systems. And then I'm going to show how I can literally take off-the-shelf tools from temporal logic games to solve a control problem from a dynamical system. And in this first shot of the problem, I'm also going to be able to accommodate, let's say, small and simple system, and the solution will be conservative. Right? Some color coding limitations in red. So what I'm going to do for the rest of the talk, I'm going to try to address these limitations. Right? So first, I'm going to show that by using, again, off-the-shelf tools from control theory, we can actually use these types of techniques to control larger systems, such as a quadrotor. And then I'm going to address the sizing, the conservativeness issue, and then we're going to be stuck to small and simple systems. So then for the last two items here, this is going to be a bit more heuristic, but I think these two directions are quite promising because I think they have more relevance in applications where one is doing formal methods there. Okay, so by finite system, in this talk I mean something like this, which very much resembles the model that I showed you for the sequential circuit at the beginning. So finitely many states, this Q1, Q2, Q3, Q4, finitely many actions. When you apply an action at a state, you can possibly enable many transitions. Like for example, in this case, if I apply U1, I enable these two transitions. At least for now, we assume full non-determinism. So if I enable transitions, I don't have a clue what's going to be taken. Versus, for example, if I had probabilities here, this would become a Markov decision process if the state was available. If the state was not available and I maintain a probability distribution over some observations, then this would become a POMDP. But for now, we assume pure non-determinism. And these are observations or properties which are true at the state. And for most of the talk, I'm going to use the logic called LTL, linear temporal logic. These are formulas in such a logic. There are three main ingredients that are used in the syntax of the logic. You recognize the Boolean operators. These are atomic propositions or predicates, and then might not be familiar with these temporal operators. This is always, this is eventually, and this is until. And the semantics is given over infinite words, over the power set of the set of atomic propositions. So this is position 1, position 2, position 3, you have a set. And I'm showing this one because it happens that actually all these three formulas are true over this word, right? So the way you look at it, you stay here at the beginning, you look ahead in time, and you can see that eventually, which means in the future, pi 2 will happen, and this happens here, so it's satisfied. And then this one says that eventually this will happen and will stay true forever. So it happens here and stays true forever. And this is actually called a strong until. So this basically says that this is true until pi 4 happens. So you check when pi 4 happens, it happened, and then you look backwards, and this is true. Good. So quite rich semantics. And this is the transition system that I showed you before. So if you look at this execution, for example, you produce exactly this word. And since the semantics of my formulas are given over such words, and this transition system produces words like this, then I can talk about the analysis problem for systems like this against such formulas. And that's the classical model checking problem. Right, so I have a system like this. It's a verification problem, and for this type of logic that we have, universal logic, actually, you check a property against all the executions, so it doesn't make any sense to keep the controls. You just keep the transitions. So again, LTL model checking means to go at every state and check whether all the words originating somewhere satisfy a formula or not, right? And it's a mature problem. It's been around for more than almost 40 years now. There's strong software tools out there to solve this problem. I'm here saying recently, means like, not until 10 years ago, people actually started asking control questions, like the dual control question would be, let's say I have a system like this, I have a control available at states, there is no determinism. Now the question is to find a set of initial states and a control policy such that when I apply it, all the words satisfy the specification. All the language satisfy the specification. So long story short, you can show that this control problem can be mapped to a game, and the idea that there is a game behind it should be more or less obvious. Right? So if I'm at a certain state, so again, I assume the state is fully observable. So if I'm at a certain state, and I apply as a player, I apply a control like V1, for example, I enable these two transitions, but the full non-determinism, I don't know which one is going to happen. So I have an adversary, the adversary solves the non-determinism, so it's gonna, he or she will choose a transition for me, and this is how the game evolves. And then the cost of the game would be the satisfaction of the formula, which turns out to be, can be a quite complicated acceptance condition for a certain type of automaton. In the most general case, a Ravel automaton, but it can also be a Buki automaton or even a simple finite state automaton, just go to the finite state. So the good news is that solutions to Rabin games are complete. So for every LTL formula, for every transition system, there is an algorithm giving me a solution. The bad news is that they're very complex, they're very complicated. There are particular cases in which you can make it simpler, but in general, these are not computationally attractive. And for the rest of the talk, it might be good to remember how the control strategy looks like. So the way it works, I'm at a certain state. Again, I apply a control as a player. Then non-determinism will be solved, and then I'm going to find out where I end up, because again, I have state observability. And then my controller will look where I end up, and it's going to make an internal transition. So what you have in here, it's actually an automaton. So it's an automaton-based control strategy, it has memory. So it's going to make an internal move, and then it's going to produce a new control to be applied, and so on. Okay, something can actually make this problem slightly more interesting. You can actually add optimality. Think of, you want to generate a control policy that satisfies the spec while also being optimal with respect to a cost, which can be defined, for example, if you assign some weight on this transition, some costs. This problem is also solved for the case when this guy is an MDP. If you have probabilities, you can formulate, for example, a problem in which you want to find a control policy to maximize the probability of satisfying an LTO spec. And you can show that this actually maps to a maximum reachability probability problem, right? Which is classical. You can solve it using dynamic programming. The only problem is that you work on with a bigger space, which kind of captures the state space of your system and the state space of the automaton that corresponds to your spec. There are also some encouraging results for POMDP, so again, in a probabilistic sense. But again, we're not doing anything probabilistic here. Good, so what I'm going to show you right now is how I can just take such an off-the-shelf game strategy and solve a control problem for a dynamical system. And I'm going to introduce the ideas through a very simple cartoon. So let's say that I have a continuous time, continuous space control system. I have a rich spec which says that I have to always avoid this region and then keep on going between this and then keep on doing this. And the goal is to find a set of initial states and a feedback control policy such that when I apply it, then all the trajectories of the closed loop system satisfy the spec. So the steps that I'm going to go through, first of all, I'm going to define a set of predicates such that I can write this spec in terms of satisfying and violating predicates. Since the regions are polytopic, all the predicates will be linear. And then obviously I'm going to map this to an LTL formula like the one that I showed you before. And I promised you I'm going to show you richer specs. So here's an example of a richer spec. More or less whatever you can say in English, if it's structured enough, you can actually map it to a formula in an appropriate logic. And then I'm going to construct the quotient of the partition produced by the predicates. So the states will correspond to regions. The edges will show adjacency relations, and I'm going to label them to show the satisfaction of the predicates by the original regions. And then I'm going to do a little work in here. I'm going to make this very strong assumption that now I can solve this type of control problems in each of the regions, right? Say that I can, for each of the region, I'm going to, I assume that I have a procedure to decide whether there is a state feedback controller that drives everything in a region through one facet in final time, for every facet. And then I have a procedure to decide whether this can be an invariant, keeps all the trajectories inside. And also for every enumeration of a subset of facets, right? So this can be, so it's a strong assumption, also can be computationally very expensive, because I have to enumerate all the possible subset of facets for each of this, for this of these regions. But again, under the assumption that I can do that, then I can augment my quotient to a control transition system like the one you saw before. Where the semantics here is that, for example, this U12 would be a symbol that labels a controller that makes this region an invariant, right? That's why I have a circle loop. On this controller from here, this symbol would map a controller that takes everything from here through this facet in finite time and so on. And then what I'm going to do, I told you that once I have a spec like this and a system like this, I can solve, I can find a control strategy in the form of a game. And then I can refine it to my original system. And you can, if you do some bookkeeping, you can actually show that there is a strong equivalence relation between this control system and this control system. So whatever I can guarantee here, I can guarantee here too, right? It's called simulation. And where does this come from is because of the way I generated the controllers, because the controllers treated all the initial states in the region in exactly the same way with respect to going to their neighbors. So that's kind of the essence of this very strong equivalence relation called simulation. But so very quickly, what kind of systems I can do that for? Because I said I'm going to make the strong assumption that I can find controllers that treat all the initial states in the same way. So here's one class of controllers. These are kind of linear systems, linear drift. The controls enter along constant directions in the matrix B. Then you have necessary and sufficient condition for driving everything through a facet. For keeping everything inside, you can also do it for a subset of facets, and also you can become slightly nonlinear. You can allow for product type nonlinearities in the drift, but then you're stuck to rectangular partitions. And there are some extensions to this, but I'm just going to mention this one now. So by using this, I just want to show you a very simple example to see how this is useful. So I'm showing a two-dimensional system which has this product type nonlinearities in the drift. So I have to use rectangular partitions. The controls enter linearly here, actually trivially like this. The spec says that I want to go to this region and then to this region in arbitrary order, but for all times I want to make sure that I don't go into this region. And the arrows show the drift, right? So it's this part without controls. So the way I do it again, I'm gonna first of all I'm gonna start designing controllers in every region to drive everything through every subset of facets to neighbors. And in the first shot of this problem, I'm only going to restrict myself to driving everything to just one facet. Why is that? First of all, it's a much simpler problem because I can enumerate the set of facets versus the subsets, all the possible combinations. And secondly, the quotient, I'm going to have determinism because I can only go to one neighbor, so I don't have to play a game. I can actually find the solution much, much easier. So if you do that, you actually end up with the controls from everything except for this region here. And the reason we couldn't find a solution from here is because we actually could not drive the system for one facet in this region because the drift was too strong, right? So we have constraints here for the control. The drift was strong, so we literally could not drive it through one of these facets, so we couldn't find a solution there. So it's interesting now if I'm willing to do a lot more computation, so now we find controllers for all subsets of facets, then we end up with solutions from everywhere. And so what happened in here basically, now we found a controller here, but we allowed control to take the states through this pair of facets, right? Because we couldn't fight the drift, so just follow the drift. And the drift can lead me to non-determinism, but I'm going to take care of non-determinism by playing a game, right? So we play a lot, you play a lot of more computation, but you actually become less conservative in the solution. So I think this cartoon kind of illustrates the idea of how the game combines with the lower level control part. So you see if I start from here, this is how the solution looks like. It happens to go here first and then to here. If I start from here, totally different behavior, right? Because the game is played differently, the choices are made differently. So again, everything is automatic, but it's kind of instructive. It goes like this. So it satisfies it in a different order, but it's still satisfaction. I don't care the way it's satisfied. Kind of interesting in here, this guy doesn't even stop in here, it actually, because it doesn't have enough braking power, the drift is strong, so it ends up stopping in there somewhere. But again, as far as I'm concerned, the problem is solved because my spec is satisfied. Good, so remember I told you at the beginning that this solution that I showed is, applies to systems which are small and simple. So let's try to make sure we understand that. Small systems because everything is based on partition, right? So I cannot do partition in high dimensions because it's going to have an exponential blow up. Simple because when I constructed the partition, I assumed this types of very specific dynamics. And conservative because this is kind of a one-shot approach to the problem, right? So I'm going to cut my system given the predicates from the spec. I'm going to construct the quotient, try to solve a problem there. If I find a solution, I can definitely map it back to the original system and have correctness. But if I don't have a solution here, it doesn't mean that I don't have a solution here. Because I might have cut my system too roughly. If I cut it finer and then update this, I'm going to have a bigger system on the discrete side. I might find a solution. But we don't do that, so that's why we're conservative. Right, so that's what I'm saying, conservative and small and simple. So now I'm just going to show you a simple trick to actually go towards more complicated systems. Any questions? No? Yeah.
I had actually a question about
Yeah.
the previous slide.
Uh-huh.
So there you have several regions. No, one more back. Yeah, so you have several more regions. So does each of those regions have one feedback controller?
Which regions?
So there's all the blue regions.
Yeah.
For
The blue
example.
regions are the regions from where I can actually find control policies.
So, but those are in the LCL description, those are all equivalent, right? You can travel through them, but you don't need to survey them necessarily.
Again, blue means where I can start from and I can have a control strategy. So
Okay.
from there, I can find a control strategy. It's just
Okay.
initial.
Yeah, okay, so let me say in this picture, the white ones, those are all equivalent in your LCL,
LTL.
LTL, right?
In what sense equivalent?
In the sense that you can travel through them without penalty and you
Yeah.
don't need to survey them
Yeah.
specifically. So does each of those have their own feedback controller based
Yeah.
on the linear or on
Yeah.
the dynamics?
Yeah.
So how do you choose where one region ends and where the other one starts? Is that a trade-off between complexity of the spec and the controllers, or?
Yeah, there is, of course. So that's, again, if I cut it into more pieces, I'm going to have more complexity.
So how is there a way to select that, or is it?
It's a good question. Yeah, so that's actually, yeah, there is. And we can discuss more about it. So I think it's even more relevant if I showed you. So I'm only talking about control, but when you solve a verification problem, the question is, so let's say that I want to, yeah, we can discuss more on the side, but for example, let's say that the vector field changed direction here. So there was some going down, some going up. This is basically where I should cut in order to reduce this type of non-deterministic behavior and bring my discrete system closer to the original continuous one. So there is a smart way in which to construct the partition with respect to making them more and more equivalent.
Okay. Yes.
But here I'm basically kind of using the control to make them equivalent, because when I'm designing my control, I'm treating all the states in the same way. But then the question, your question is very valid, and I'm going to show something else very soon actually. I'm going to cut it in such a way that the likelihood that I find the controller making the two equivalent is high. Did I answer your question?
Yeah.
Okay.
Thank you.
All right, so I said I'm going to just use some simple trick to allow me to use that as is to look at a bigger system and more complex. So I'm going to again illustrate this through an example. This is a like the simplest robot that you can look at, right? It's a unicycle, three-dimensional. The state space is the coordinates of frame that's centered at the robot and aligned with its axis. And then the third one is the orientation of the robot. So this is how the dynamical system looks like. These are the two controls. One is forward speed, the other one is rotation in angular speed, rotation in place, right? And I have some constraints for these controls. So if you just look at this and I want to apply the framework from before, even this very simple system wouldn't work, right? Because I only had linear and slightly multilinear. And this one has cosine and sine, so it's ugly. But then you can use a trick that, it's very popular. I can define a convenient output. Like, for example, if I take a point that's displaced by epsilon along the nose of the robot in this direction, and I denote this as an output, and I differentiate it once, it happens that I see the original input on the right-hand side from in one step, which means I'm doing input-output linearization and relative degree is 1. Good, so then I can focus on this system then, which looks simple enough to apply the method from before. Also interesting enough that this is how the two controls, the original control and the new one, are related. This is a rotation matrix. This looks like this. So you can actually, with some conservatism, you can construct a constraint set for this one such that when this is true, then this one is true. So you guarantee the original constraint for the original system. Okay, so as I told you, very simple and very straightforward. So then you can get things like this using this method, right? So this is a unicycle, so it's not a, but again, computation is done for a fully actuated point, which is somewhere at the full nose of the robot, but then you have more complicated dynamics in there. And then, remember I promised at the beginning we're going to go back to the quadrator, so a very related notion to input-output polarization is differential flatness, right? So I would say the most traditional model for the quadrator, it's a third-dimensional control system, and then this happens to be differentially flat if you consider as output the 3 positions and one of the orientations. So differentially flat means that you can exactly reconstruct the input and the state as a function of output and enough derivatives of the output. Right, and they can come up with this scheme, which is actually quite popular in the quadrator community. When you see all this aggressive maneuvering, this is how it's done. If you want to generate a trajectory, I'm going to draw like a lot of points that I want my quadrator to go through. And it happens that the position is actually one of the flat outputs, so it's prescribed here. And then go through this inverse of the differential flatness map, we can come up with the desired inputs and reference states. And then you have an SSV controller to make sure that you actually follow those states that you want to achieve, right? So again, this is more or less classic. And then what I'm going to do, then I'm going to apply my procedure in the space of the differential flat outputs, as I did before in the space of the output which was obtained through input-output linearization. So this is the example that I showed at the beginning that I promised I'm going to show at the end. So in this particular case, we actually produce a 2-dimensional motion. We assume this guy flies in the plane. So we discretize in 2 dimensions, and then we do all this assignment of vector fields in such a way that I have equivalence between my dynamical system in 2 dimensions and the quotient. We play the game, and then this is what we generate. In this particular case, it's slightly more interesting because what it does, it actually is supposed to come from here and then keep on going there or there and do this infinitely often. But then locally, it detects obstacles, it detects these guys that can go on and off, so it has to react in such a way such it doesn't screw up the global plan. So there is a way, using Lyapunov type functions, to actually ensure that you can do that. And I would be happy to tell you more if you want to learn about this. And it can become more sophisticated on the discrete part, like multi-agent. In this particular case, we have, just going to show you this movie while I talk about it. Charging stations where the robots can automatically take off and land, and then the question is, can you have somebody always in the air and satisfy a spec like this, which is slightly more complicated than what you saw before, because now you also even have time deadlines, and you take into account the battery life for each robot. But in essence, what allows us to solve a complicated problem at the finite part is the way we solve the way we go from continuous space to discrete space. Right? This kind of assignment of vector fields, which ensures equivalence between the dynamical system and the graph at the top. But I told you I'm going to be high level, so. All right, so I would say this one is still conservative because, again, it's based on a one-shot partition of my control system. So if I cut it roughly and I find a quotient and I find the solution, I can always come back and be correct. But if I don't find the solution, it doesn't mean anything for my original system. It means that I'm conservative. I should come and maybe cut it more and look for more solutions. So that's what I want to show right now. I want to show how I can address this conservativeness issue, but then I'll have to pay the price and actually come back to small and simple systems. And again, I don't have many details, more like an overall story, more like a review. So I'm going to consider now discrete time. So this is a discrete time linear system. And let's say that I have a set of predicates which are linear. And I'm going to assume that the control is restricted to a polytopic set. And here the question is the same as before. I want to find a set of initial states and a control policy such that when I apply it, then all the trajectories of the closed loop system satisfy a temporal logic spec, which in this case it's actually a fragment. It's called syntactically co-safe for technical reasons. So basically we proceed as before. So we start with the rough partition, which is given by the specs. And then we try to construct controllers to take us from one region to another in infinite time. But different from before, if we cannot, then we find a smart way to refine it, and we refine it guided by the specification. That's why it's called automaton-based partitioning. Right? So again, I'm not going to show details. But what's interesting, if you look in the technical paper, is that here we have a notion of completeness. So as long as you work with discrete time linear systems, and as long as you restrict yourself to these types of specs, and as long as you construct the polytope to polytope controllers in the way we recommend, which is actually not bad, it's actually not very conservative, then you have a proof that this partitioning process will terminate. And you actually can come up with the largest set of initial states from which the specification is satisfied. Then I have a little example in here. So this is what syntactically co-safe means, that you always end up somewhere, and this is where you terminate. Even so it's an infinite time. Satisfaction is infinite time. So the spec basically here says that you want to go to the target. Before you go to the target, go to A or B. Always stay away from O1 and O2. Right, and I'm looking at a simple double integrator, and the question is to find a set of all initial states satisfying this. And again, the good news is that you can find all. And I have a movie showing that, which actually I just realized it didn't work last time. So yeah, okay, so you cannot see it. But again, if you're interested, I can make this available to you. Would show partitioning using lines in here, and end up with a kind of half of this covered by a set from which you can satisfy this spec. And very briefly, I want to show a connection to optimality. I'm going to come back and show a better one later on, but a connection between optimality and correctness, starting from what I just showed you before. Right, so I'm kind of showing like a classical MPC receding horizon control problem, right? So this is discrete time, linear system, constraints both on states and the controls, and I'm going to assume that I have some reference trajectories in state and control, and the goal is to stay close to those, right? So I have a cost which penalizes deviations from those reference trajectories over a horizon n, and let's assume the trajectories only become available over a horizon of length n. So in order to solve this problem, the classical approach is the MPC or receding horizon, right? So you optimize over the length of the horizon, find the sequence of optimal controls, apply the first one, and then keep on going because more reference trajectories become available and so on. So now the question is, what if I want to add safety on top of that, right? So I want to have optimality, but I also want to be safe. And in fact, I want safety to come first. And I'm going to specify safety, again, as a temporal logic formula over linear predicates. So can I satisfy this and also do as good as I can in terms of optimality? I'm not going to show, I'm just going to show you examples in here. So there is a solution which is not amazingly good, it's conservative, but it's correct. Right? So I'm just going to show you some examples to just appreciate this compromise between optimality and correctness. So again, the same double integrator from the beginning, same spec, I want to go here and here or here before I go there. And in this particular case, I have a reference trajectory, so I want to stay as close as possible to this green one, while at the same time satisfying the, and that's hard, the constraint of satisfying the temporal logic spec is hard, I cannot violate that. So this is what I get. The red one in the case when the left of the horizon is 2, so I don't have much to optimize. So even so I'm satisfying, I'm not doing very good at staying close to the green one in terms of optimality. If I have a longer horizon, I do a bit more computation, but I'm actually doing much better in terms of staying close to the green one. And it's interesting to note here that the reference trajectory in these two cases is actually satisfying, so I don't have to play any game against, I don't have to compromise between optimality and satisfaction because the reference trajectory is actually satisfying. Which is not the case in the last picture here, where the reference trajectory is actually not satisfying. You see it goes to T, but it doesn't go to A or B. And then what my controller tries to do its best to satisfy, so it barely goes here and then it barely goes there, trying to stay as close as possible to the green one, right? So it is safe and as close as possible to the green one. Okay. All right, so I told you I'm going to now try to, with a bit of, it's going to be a bit more heuristic, but I think what I'm going to show you now has more promise in terms of looking at methods which are not conservative and also might apply to real systems which are can be large and dynamics can be very complex. So this is what we did before, right? So we basically had some environment and some specs, and then we cut the environment, we did partitioning, produced a quotient, and on that quotient played the game and refined the solution back to my original system. So the main problem here, which drives the complexity step, is the partitioning process, right? And in the robotics community, people call this cellular decomposition, right? They have a workspace, and then they cut it into pieces, and then they want to go from one place to another. They cut everything into pieces, look at the quotient of the partition, and find the path on the graph from one point to another. To solve this problem, they came up with the sampling type procedures, right? I guess most of you heard about RRTs, RRGs. So other than cutting the environment into pieces, you actually generate samples and incrementally construct a graph with the hope of eventually finding a path in this graph or tree from the initial point to the final point. So the question is, can we do the same thing here in the formal synthesis framework? Can we somehow, let's say that I have a spec over these regions, can I incrementally grow a graph or a tree and incrementally look for the satisfaction, for a path that actually satisfy a rich topology spec rather than just a path going from one place to another? So this is the problem that we looked at, and so very briefly the answer is yes. And what's interesting about this is that the problem that you need to address is scalability, right? So this sampling procedure can be extremely expensive. Once you grow this tree, it becomes larger and larger. It grows very, very fast, and the problem of looking for a satisfying path becomes very expensive. So the question is, can we come up with something that's incremental? So something that looks for the existence of a satisfying path that scales with the number of samples that are generated at a certain iteration versus with the size of the whole graph, the size of the whole tree. In this particular case, it's a graph because we need cycles, because that's how LTL formulas can be satisfied. You need to have a prefix and a suffix that's repeated infinitely often, so we need cycles. Right, so again, so Christy actually did the work, it's sitting right there, so we can answer more questions if you guys have any. So there is a way to do this incrementally, which actually kind of is the main thing, which makes this problem feasible. And also it's probabilistically complete because it more or less inherits probabilistic completeness from the RRT algorithm, or the RRG in this case. So just to give you a brief idea, so here's a 2D example with the spec, which basically says that I have to visit the corners infinitely often and always avoid the obstacles. And so this is how long it takes to generate, to construct a graph and then to find a satisfying path in this graph, like about 7 seconds. If you go to 10 dimensions in still a rectangular world, spec slightly simpler, then you end up doing this in 17 seconds, right? This is the statistics. If you go to 20 dimensions, where again there is even in 10, I think there is no hope to partition. So if you go to 20 dimensions, and again for a simpler spec, then you have an average of 7 minutes, right? But again, this is something that you do offline, so it might not be that bad. And you can also combine this with the local planning. So what I'm showing here is a robot which has some offline global information before deployment. So it knows that it has to visit these guys infinitely often and stay away from the dark gray obstacles. But it also has a local sensing region around it, and when it moves around, it detects other obstacles or maybe things that it wants to catch, tries to trap. So whenever it says something like that, then it has to replan, right? So it moves on the graph, which ensures satisfaction of the global spec, but it has to react to these things. So the way it does it constructs a tree locally, really quickly, go solve that problem, and then come back to the graph. So a technical issue here is that how do you come back to the original transition system to make sure you don't screw up the global spec, right? So that's actually something that we did. I think this the movie actually shows how the local tree is grown when local events are detected. Like for example, that particular case, the green disk is something that I guess you want to catch, right? So you grow it, and then you get there, and then once you get there, then you have to find your way back to the original graph. And here's a more realistic example. This is the right arm of a Baxter, 6 degrees of freedom. So Christy has a movie that he sent me, and I couldn't even run it very well. But in this picture, you can actually see the global pass that was generated, and then he's moving a ball around, which is an obstacle, and Baxter reacts to that, avoids collision with the ball, but always comes back and achieves the initial task, which in this particular case was to keep on visiting regions 1, 2, 3 infinitely often and stay above the table. Good, so what I showed you, in the example that I showed you, you can actually look at large systems, right? The 6 degree of freedom using formulas, I think it's quite good. So what I want to show you next is an alternative to this, but which is now we're going to go back to simpler systems. But what's nice about this one that I'm going to show is that it has a way to seamlessly combine optimality and correctness. Right, and this is actually work done by Sadra, which is also sitting here. So I'm going to switch a little bit. So the logic that I'm going to use in this case is slightly different. So as before, we still have the 3 main ingredients in the syntax of the logic. We have the Boolean operators, we have the predicates or the atomic propositions, and we have the temporal operators, but the temporal operators now are timed. Right? So now when I look at this formula, this basically says that for all times between T1 and T2, I want this to happen, not for all times from 0 to infinity. And this one says that for some time, so eventually, so for some time in between, there exists a time in between T3 and T4 where this is true. And the semantics of this formula, of this logic, which is called STL, by the way, is given over signals. And I have here an example of a signal. And we have the usual Boolean semantics that we had before. Like for example, in Boolean semantics, this formula is true over this signal because you can see that for all times in between T1 and T2, this signal is actually under 2.5, which is this line over here, right? And also in the Boolean semantics, this formula is false because it says that there exists a time between T3 and T4 where the signal becomes larger than 3.5, but that's not the case because 3.5 is right there, so it never goes above the threshold. But what's nice about this logic, and that's what we actually exploit, and that's why I'm showing it in red, is that it has a quantitative semantics. Quantitative semantics means that given a signal and a formula, I can come up with a number which tells me how well I satisfy or how badly I violate. Right, so positive values for this means satisfaction. The more positive, the more satisfaction. Getting close to 0, you start having problems. It becomes negative, it's violation. So again, to exemplify here, for example, so again, this one in Boolean semantics was true. In this quantitative semantics, it has a value of 0.01, right? So it's positive, it's consistent with having Boolean satisfaction. 0.01 means that it's this gap over there, it's actually 0.01 that you can really see. So that's how close you get to violating, or the margin you have for satisfaction. And in the other one, the quantitative semantics is negative because again, it's false. And apparently that length over there is 0.2. So again, that's how much you would need to satisfy, or that's by how much you violate. And these two properties here is actually what allow us to actually combine optimality and correctness in the next slide. Boolean satisfaction of STL formulas of linear predicates can be mapped to a feasibility of a larger milk. So it can be large because you're going to have one integer more or less for every discrete time in the on your timeline. So and this depends on the horizon of your formula. And the second property is that this robustness is actually a piecewise affine in the integer and continuous variables from the milk. All right, right, so with this in mind, I can actually simply formulate this optimization problem, right? So let's say that I want to minimize or maximize the cost, which is linear in the state and controls. And I want the dynamics of my system to be more or less linear, but linear on the continuous side. You can have complicated things on the discrete side, right? So this can be piecewise affine, or it can be mixed logical dynamical system, like a hybrid system, but with linear continuous dynamics. And then this is my correctness spec. So any STL spec over linear predicates in this. Right? So remember, this is going to be linear over everything in the milk. This is linear, so this is a big milk, which again can be solved even if it's very, very high dimensional. Right, so again, example, this is a simple integrator, right? And in plane, so this is two-dimensional, and my specification basically says that I want to go to C within 30 time units, and then I want to go to A and stay there for all times between 40 and 50, and within 40 time units I want to go to B and stay there for 10 time units. Good? And I have a cost which tells me that I want to, let's say, minimize fuel consumption, so it's the absolute value of U. So again, you map it to a MILP, and then you solve the problem, and you end up with a solution which looks like this, which is kind of what you would expect to get, because, so again, obviously you're going to have satisfaction, so if you look carefully, it actually goes to all this and it spends enough time that it meets the deadlines. What should worry a little bit is that the satisfaction is a bit fragile, it's not robust. But that's because I'm trying to minimize fuel consumption, so I'm trying to move as little as possible. So that's the way to move as little as possible and satisfy, right? But again, not being robust with respect to satisfaction of a safety property, it's usually not a good point, not a good thing to do. So what do? You can actually play tricks such as adding, remember robustness is also linear in state and control. So basically, I can augment my cost, putting robustness in there. So you can see here if robustness becomes negative, this term will become large positive, it will dominate this one. So once I have problems with satisfaction of my spec, this is going to kick in. Forget about fuel consumption, just pay attention on satisfaction, right? So then you would end up with something like this, which looks better, right? You go more towards the center of the regions, which gives you more robustness. When you can make this problem more interesting, you can now think of doing things in infinite time. Let's say that you want for all times to satisfy a spec, which is over finite time. And then again, you have a linear system, and then you have a linear cost, and then you can come up with the better cost than what I showed you before. So for example, this is the cost that ensures fuel consumption, and this one would only kick in when we have problems with the correctness. Right? So if robustness becomes here negative, then this would become, if M is very large, it's going to become large positive, so this will take over the optimization problem. So this combines robustness of satisfying the correctness with optimality of whatever you're interested in achieving. So what's also nice is that, actually this is Sadra's work, again Sadra sitting there, you can, as in any type of problem like this, which looks MPC-like, you have to take care of terminal constraints and they can be ensured. So I guess the examples are the best way to look at this. Again, a kind of double integrator kind of system, and this specification, if you look carefully here, basically says that what I want to do, I want to keep on oscillating between these two grid regions, and I want to make sure I do it fast enough. So within 4 time units, I have to switch. So keep on switching between these two regions within 4 time units. I also and I want to minimize fuel consumption. I want to minimize that. So, and I'm also going to add some noise in here because I want to at some point put some noise in there and see how robust the control procedure is with respect to additive noise. So this is what happened if you don't have any noise and you solve the control problem with this cost over here, right? Which again is what you should expect to get. What you get in here is you go from one region to another. It doesn't make any sense to go towards the middle of the region because there's nothing penalizing, there's nothing encouraging robustness, and I want to move as little as possible, so I'm going to go to the edge, move as little as possible, stay there for 4 time units and keep on switching. If I use the same control strategy but I add some noise, I'm in trouble, right? You see there's not satisfaction anymore. However, if you go back and then use this cost that we propose, which is this one, then it's much better, right? So we have this robustness. Whenever there is a problem with satisfaction, the big M term kicks in and focuses on safety. And again, this is one of the motivation examples that I showed at the beginning. I only have one slide on it just to show that this formal methods procedure scales, right? Because that's, for those of you working in this area, actually kind of in the boundary between dynamical system and formal method, scalability was always a problem. You can always write down correctness proofs, but coming up with procedures that scale, that was a challenge for a long time. So I'm kind of proud of this example that Sandra produced. So again, this is a 53-dimensional dynamical system, so quite large, right? It's a piecewise affine system, and which again captures this is a traffic network with like 53 links. It has intersections controlled by traffic lights. Also, it has ramps, and so the spec basically here says that for all times you want to satisfy this, which is a conjunction between you want to be congestion-free. So the congestion-free condition can be written as a polytopic invariance. You want to stay inside a certain set. And this also said that if density ever reaches 3, then in 3 minutes should become less than 3. You can make it this region, right? So the good news is that, again, this quite large problem can be solved in 5 seconds. And again, you have 50 plus state variables initially. The milk that you produce after you map everything to a milk ends up to being in like 200 and something dimensions. But it's solved very, very fast. Good, so that's kind of what I wanted to show you today, right? So we started from off-the-shelf tools, from automata games, and I showed you how I can solve a problem for a dynamical system, but it was very conservative, only applied to simple systems and small systems, and then using input-output linearization and differential flatness, you can actually look at more complicated systems, and a lot of people in the robotics community do that. And then we worried about completeness, but we ran into pretty big complexity problems. And then these two techniques, which I'm actually showing in bold, I think they have a lot of promise, because you can actually now look at, I would say, realistic applications, at least in robotics, also biology, and you can still have some sort of a correctness guarantees. And that's all I have. And again, 2 of the people who did work a lot in this are actually in the audience, and actually they're part of MIT right now, so that's I hope I have you guys there, right? So that's Sadra, and that's, where's Christy? I don't have Christy. No, I have Christy, so thank you.
Any questions from the audience?
Yeah.
Is there a way to think about optimality on the global side when you design the feedback flows in the polytopic partition? So it seemed to me that the trajectories you have at the end are kind of yeah. In each piece you do whatever is best for that piece, but then you don't really care about the trajectory as a whole.
So again, we put correctness first. So that's what we do. So we have some sort of partition. The partition is given by this step. It's given by correctness. So we don't have any freedom to do the partition there. And then what I want to do, what I care about, is put the equivalent sign between x dot equal to f of x and mu and the graph. And that's why I'm designing my controllers. So again, there's no optimality there. We can do a little optimality on the graph. So once I find paths on the graph, I can find paths that are, shortest with respect to how much I travel. And actually I have a paper which we do that. But so this is actually very, very bad in terms of optimality. Like I can do a bit of optimality, but the problem, like as you said, let's say that I want to be correct and actually find something that's optimal in the topology of the original space, that's a different issue. And we've never done something like this. There might be something to be done, but again, at least in our group, we're always interested in correctness first. I think what we have towards the end, that's why I like Sadra's method, because it's just like seamlessly combination of optimality and correctness. Everything is just one big program.
Yeah.
And then you can, using your weights, you can give more weight to safety, more weight to optimality. His trajectories are actually more or less optimal with respect to the optimality that you care about, which can be energy or time, etc. Yeah.
I'm not saying the speaker again.